Okay, so in the last class we were looking at mm, writing down symmetries in such a way that they are not dependent on a specific choice of coordinate system. And what we did was that we wrote the symmetries in the form of what is called a killing vector. And if you write down symmetries in terms of killing vectors, then they are independent of choice of coordinates. So therefore, if you because they satisfy some covariant equations, so if it is true in one coordinate system, it is true in any other coordinate system. And then we looked at certain class of killing vectors. For example, if the metric has translational invariance, then we showed that if the space has translational invariance, then you can always write down one metric in which you can see the translational invariance very easily. But generically, you would write down a killing vector, which at a particular point would corresponds to would take a constant value. Okay, and so this basically is a vector because xi carries index alpha. This beta tells you that there are as many vectors as the number of values that beta can take, and beta of course also takes the same number of values that alpha does. Okay, so if you have now of course this is not necessary that beta should always take the same values of alpha. For example, you may have a space which is four-dimensional x, y, z, t, and you may have only time translation invariance but no space translation invariance. In that case, beta would take only one of the four values. Okay, so that is the reason why this counting parameter doesn't have to be the same as the vector value, but it cannot be larger than that, as number of translational symmetries would be equal to the number of dimensions of the space. Okay, then we looked at the rotational symmetry, which is a killing vector which should leave the point about which you do the rotation invariant. That is why xi alpha x0 was 0, whereas its derivative was not. Okay, so that was the other example that we studied. And the largest number of values that these largest number of killing vectors that the space could have with rotational invariance is d into d minus 1 by 2, whereas the translational generators would be d. Okay, so if the space is both translationally invariant and rotationally invariant about a point, then total number of killing vectors that we would have is d into d plus 1 by 2. Okay, so this was the computation that we did last time. Okay, just hold on, I just got some message which may be important for the class. Okay, we may have disruption around 12ish. I will switch to my phone network at that time.
It's all right.
Okay, so so the maximum symmetries that you could have is d into d plus 1 by 2, which includes homogeneous space, which means translational invariance, and isotropic space, which means rotational invariance about a point. Okay, spaces of this type, which have d into d plus 1 by 2 killing vectors, are usually referred to as the maximally symmetric spaces. Okay. Then we looked at Minkowski space as an example, and we showed that in case of Minkowski space, because the Riemann tensor vanishes, you can show that the killing equation becomes trivial. It's just second partial derivative of the killing vector equals 0, and the solution therefore is that the killing vector can be at most linear in the coordinates. Okay. Now, notice one thing that, like, of course, this computation is being done locally. Okay, so therefore, it doesn't really matter how complicated the Minkowski space metric could be in some bad choice of coordinate system. Okay, but if you want to do a global computation, you may have r is equal to 0, but you may have to put a connection piece inside these covariant derivatives. But nevertheless, you would find that the answer is not very much different from what you would get locally. Okay, fine. So if you impose the killing vector condition on this, it tells you that B alpha beta would be antisymmetric tensor. And this is something we already know. A alpha is a transition generator and B alpha beta are called Lorentz transformation generators. Okay. Now, clearly, not all metrics would be maximally symmetric. Many metrics, in fact, may not have any symmetry at all. So there may not be any killing vector defined on that space. Okay, but if you have any initial data which is some killing vector and its covariant derivative, then you can show that this initial data is sufficient for us to determine the killing vectors at any other location in the space. And to see that, what we did was we looked at the double covariant derivative of the killing vector, and we showed that on one hand it gives you Riemann tensor, on the other hand you can show that it would contain terms which would involve we basically take one more derivative of that quantity, and it involves the derivative of the Riemann tensor. Okay, so let me just step back a little and show it again. That double covariant derivative of xi is related to the Riemann tensor, but if you take a commutator acting on a covariant derivative of xi, okay, that can be rearranged in terms of, given that the commutator of covariant derivative gives you Riemann tensor, you can write it in terms of Riemann tensor times the covariant derivative of psi. Okay. On the other hand, you can just open it up and you can show that quantity has the property that this double covariant derivative acting on xi would involve Riemann tensor, and this covariant derivative could act on the Riemann tensor. Okay, so you get, from left hand side you get 4 terms, on the right hand side you have only 2 terms. Okay, so you can kind of collect these terms together. This equality of course has to be valid. Okay, so you can kind of rearrange these pieces. Left hand side involves only derivative of Riemann tensor, that means this term and this term. Right hand side contains terms where the covariant derivative acts on xi. So there are only 2 terms here, and these 2 terms add up to get you an expression, something like that. Okay. Now remember that this left hand side is antisymmetric in gamma and delta. D delta of r involving gamma minus d gamma acting on r involving delta. Okay, so that means the antisymmetric part of this expression, okay, is the only thing that we should be really looking at. Okay, so what we'll do is we'll basically kind of impose a condition on the right hand side of this equation, take the antisymmetric part of that. Okay, fine. Now suppose you are looking at a space which is maximally symmetric. Okay, then of course you would have a situation where you have one killing vector which would just vanish at a particular location. Okay, and when it vanishes at particular location, remember we had, maybe I just step back a little and show it again. This is a Lorentz transformation killing vector which has a property, a rotation killing vector, whatever you want to call it, which has a property that the killing vector is 0, but its derivative is arbitrary. Okay, but its first derivative is arbitrary. Okay, so if you use this condition, okay, if you look at this killing vector, Then it's too slow. If you use that killing vector, then the equation that we get here would have xi sigma equals 0, and the right hand side therefore has to be 0. Okay, because we have chosen a killing vector which vanishes at a particular point, but its covariant derivative is arbitrary. Given that its covariant derivative is arbitrary, this quantity cannot vanish, and therefore the quantity inside the parenthesis should be 0. Okay, fine. So the statement that we really need to look at here is the following: that because of the antisymmetry between gamma and delta, you actually need to antisymmetrize this quantity, and that is a quantity which should vanish. Okay, so therefore we will kind of state this equation as this is equal to the same expression with gamma delta swapped, and looks like I haven't done that. I'm sorry for this. Okay. Just give me a second. Yeah. Correct that equation. But so
Sir, I don't understand
yes,
246, page number 246.
246. Yeah.
Okay. Oh, that was in. Okay, you can go up. Yeah, just one slide up. Yeah,
This one.
from
Yeah.
here and the second point written for the maximally symmetric space, we
Yeah.
can find a. Yeah,
Yeah.
I mean,
So
how does
yeah.
it follow from the above equation?
Yeah. So what I was trying to say was that okay. So there are two things. First thing is that, like, if you know the killing vector, okay, then this equation allows you to determine the Riemann tensor. That is this statement. Okay. So you don't have to kind of you don't explicitly need the metric. If you knew the killing vector, okay, you would be able to determine the Riemann tensor. The second statement is the following: that if the space is maximally symmetric, okay, then the maximally symmetric space has d into d plus 1 by 2 killing vectors. Of those killing vectors, there exists one class of killing vectors which vanishes at a particular point. Okay, that if you use that killing vector, then this equation would have its left hand side vanishing, right? Because this killing vector would vanish at a particular point. You just go to that point, this left hand side of this equation would vanish. Okay, but the
Okay,
fact that
now I got it. Since the
yeah,
right hand side is, I mean, del beta or xi alpha is arbitrary, so left the coefficient of that should be 0 at
yeah,
that
so
point.
exactly, so the parenthetic quantity should just vanish. Okay, but
Okay,
it
sir.
cannot vanish just like that. In the sense that like only place where it will actually vanish is because this expression on the left hand side is anti-symmetrized in gamma and delta. So you anti-symmetrize that in gamma and delta and set that to 0 really. Okay, so that is this equation. Okay, so now you see the thing that if gamma delta swapped at all the locations, and this equation has to be equal. Okay, fine. So what you do is that you can contract say rho and gamma. So if you contract rho and gamma, then delta rho or delta gamma, whatever you want to call it, that is equal to d. So that will give you d here. Here you just if you contract gamma and rho, then you replace gamma by delta here. Okay, so you get a delta here, and then if you choose similarly gamma will be replaced by beta here, and so on. So you just do those replacements by setting gamma is equal to rho everywhere. Okay, and then you use this delta function. So that gives you this equation, and this equation has can be massaged and simplified. One of the things that you will realize that like there are some terms which are identical. Okay, so for example, you have r delta beta alpha uh, here as well as here. Okay, uh, and what you could do is that like you can arrange these quantities in a particular fashion. Okay, for example, you look at this term r alpha delta beta, r beta delta alpha, and r delta beta alpha. These three terms can be written in a way in which three indices are cyclically permuted. Okay, if you write it in that form, then you know that the cyclic permutation of Riemann tensor with these three indices is 0 by Bianchi identity. Okay, so therefore this and this term just cancel out, and these two terms are identical, so you get d minus 1 times r sigma delta beta alpha is equal to the Ricci tensor pieces. Okay, so that is the equation that you get. Okay, so what you can do is therefore write down, you can pull this index down and replace these deltas by the metric. Okay, so that is the equation. Okay, so are you with me on this?
Yes, sir.
Okay, so this is how the equation that we obtain. If the space is maximally symmetric, it has rotational isometry, which has been used to simplify this equation to this particular form. Okay, fine. Now you also have a maximally symmetric space in which xi itself can take arbitrary value. Okay, that is of translational invariance, right? Xi takes arbitrary value, but its derivative vanishes. Okay, in that case, if you go back to this equation, then you will see that the right hand side now vanishes because its covariant derivative vanishes. But left hand side, since xi takes arbitrary value, this parenthesis should vanish. Okay, so we will impose that condition. Both these conditions are true only for maximally symmetric spaces. We are not looking at the spaces which are not maximally symmetric. Okay. So we will set this equal to 0 because we are looking at a different killing vector for the space. Okay. Again, we can do the same kind of contraction. Yeah. Sorry. Something is wrong. I didn't want this equation to repeat again. Okay, I have to correct this page. This set of equations are not there. They are like okay, but yeah. So let's skip this for the moment. There's I don't want these equations at all. Actually, they are repeated for no reason. Okay, but coming back to this thing that let me go back to this equation. Okay. So now remember, this equation is antisymmetric in gamma and delta because the Riemann tensor has a property that it is antisymmetric in first two indices and antisymmetric in last two indices. Okay. So what we could do is that we can impose a condition on antisymmetry on these on the right hand side of the equation. Okay. So that would tell us that you can write down R the right hand side of the equation to be in this particular form. Okay. So this equation, if you look at it, it is just setting the symmetric part of the right hand side equal to 0 because it has to be only antisymmetric. Only antisymmetric piece agrees with this thing. Pretty bad. Just a second. Okay. So what you actually get is that from here you can further contract alpha and gamma to get an equation which is R beta delta minus D times R beta delta is equal to R alpha alpha, which is scalar, okay, times G beta delta plus R beta delta. Okay, that is the equation that you will get by doing a contraction of alpha and gamma. Okay, so this is the equation. There was a typo in the equation, that's why it was not looking good. Okay, so all we are going to do is basically collect R beta delta pieces together. Okay, and that will give you an equation which tells you that you can write down a Ricci tensor in terms of Ricci scalar. Okay, so why am I doing this? I'm doing this because what we have done is we have established that for maximally symmetric space, a Riemann tensor can be written in terms of Ricci tensor, right? That is the first result that we obtained using the rotational killing vector. Okay, then we use translational killing vector to determine next condition, which tells us that the Ricci tensor can be written in terms of Ricci scalar. So what we can do is we can combine these two results and write down the Riemann tensor in terms of Ricci scalar, which is same as R alpha alpha, okay, times just product of matrix. Okay, this follows from the earlier equation that we had written down, that R Riemann tensor can be written as Ricci tensor times metric. Yeah, Ricci tensor times metric minus Ricci tensor times metric. Now you write down Ricci tensor as Ricci scalar times metric. So therefore you can pull the Ricci scalar factor out, and then you get metric two products G alpha delta G beta gamma minus G beta delta G alpha gamma, whole multiplied by the Ricci tensor scalar divided by D minus 1, and there is an additional factor of 1 over D. So that's why you get 1 over D into D minus 1. So you get 1 over D into D minus 1 because of this factor. Okay, fine. Now what we'll do is we will use the Bianchi identity that we have already studied, that is the covariant derivative of the Einstein tensor is equal to 0. Okay, but we know that for the maximally symmetric spaces, the Ricci tensor is proportional to Ricci scalar. So you can kind of put that factor in and you get a result which is like this. Okay, that covariant derivative of 1 by d minus half times g alpha beta r is equal to 0. Okay. Now, this quantity would be 0 only if covariant derivative of r is equal to 0, because covariant derivative acting on g is anyway 0. Okay. So, covariant derivative of acting on r, but r is a scalar. So, therefore, a covariant derivative acting on a scalar is same as ordinary derivative acting on a scalar. Okay. So, therefore, as long as d is not equal to 2, if d is equal to 2, of course, this term vanishes. Okay. So, then life is little different. Okay. But as long as d is not equal to 2, you can show, therefore, that for the maximally symmetric spaces, the Ricci scalar is constant. Okay. Because its partial derivative is 0. Okay. Now, you can step back and realize that if Ricci scalar is constant, then Ricci tensor is proportional to metric, and Riemann tensor is proportional to products of metric. Okay, because this is a constant and this is a constant. Okay, so so you can see that it's a very special class of matrix in which Riemann tensor is just constant multiple of just products of metric components. Okay, is that fine?
Fine, sir.
Okay. So let's define this constant to be some number so that we can get rid of this d into d minus 2 or minus 1 sitting in the denominator. So suppose you define r is equal to minus of d into d minus 1 times some number k. Okay. Then our Ricci tensor would look like minus d minus 1 times the metric times k, and Riemann tensor would become minus k times just product of two metric components. Okay.
So why a particular choice of minus in R? Minus K, why
Oh,
minus K?
well, this would help us in kind of setting up, you know, yeah, you'll see. I mean, like, I mean, we want k being positive correspond to, say, uh, spherical geometries, and k being negative corresponding to hyperbolic geometries. So if you do it this way, it will work out. Okay. Otherwise, it would look the other way around. Okay.
Okay, sir.
We will see these examples.
So it is a statement that negative curvature and positive curvature, that thing.
Yeah, exactly. Spatial curvatures that we are looking at. Yeah. Okay. Fine. So the generic way of obtaining maximally symmetric spaces is to embed them in higher dimensional flat space. Okay. So what you do is you start with a higher dimensional space. The higher dimensional space is flat. By flat I mean it doesn't have to be diagonal completely. If it is diagonal, of course, life is even simpler. But GAB doesn't have to be diagonal, but CAB that is written down out here is constant d by d matrix. Okay, it's a d by d matrix, but it is with constant entries. And K, it's the same K that we are writing down here, is K inverse times dz square. So this is like one extra dimension. So it's like, you want to take a two-dimensional surface and embed it in three-dimensional space. Exactly like, a sheet of paper in three-dimensional space. Okay, that is the kind of stuff. Okay, you just have to generalize it to higher dimensions. So like, for example, if you're looking at four-dimensional maximally symmetric spaces, you embed it in 5 dimensions. Okay, fine. Now, the embedding of the maximally symmetric space is very special. It's not like, you write down a random function. Okay, of course, you can write down a random function to get a four-dimensional space embedded in five-dimensional space. Nothing stops you from that. But maximally symmetric spaces are very special. You write down a quadratic equation like this: k times c alpha beta x alpha x beta plus z squared equal to 1. Okay, so this almost looks like an equation for a sphere. Okay, and it is in fact an equation for sphere, provided of course k takes positive value, right? If k is negative, then of course you can see that there is a relative sign and it looks more like a hyperbola. Okay, is that fine?
Yes, sir.
Yeah. So what we'll do is we'll kind of take this equation, and we can eliminate z from this equation, right? We can write down z squared is equal to 1 minus all this stuff, take square root with a plus minus sign. You have two solutions for z. write down dz for that, you can write down dz in terms of dx. Okay, and then you can get rid of this dz squared and write down the expression in terms of dx alpha and dx beta completely. Okay, if you do that, okay, then you get the following thing. Okay, dz squared, this is not a very difficult thing to do. Dz squared would have, remember, z would have had a 1 minus this quantity whole square root. Okay, so if you write down dz, that square root goes down and a quantity sits in the numerator. Okay, but when you square that, then the term in the denominator is not a square root anymore, and the term in the numerator is squared. Okay, so that's how dz squared will come. It's a kind of a few steps calculation from here to there. Now you take this and put it back here. Okay, if you do that, then you get a metric written completely in terms of x alpha coordinates, and there is no z at all. Okay, if you do that, then you get a metric which looks like this. It's not very difficult after all. Once you have determined dz squared, you are just substituting it here. This k squared becomes k here simply because there's a k inverse sitting around in this metric. Okay, fine. So this is how the metric is going to look like. So the metric component G alpha beta is C alpha beta plus K upon the denominator times C alpha sigma X sigma C beta sigma beta rho X rho. Okay,
Sir,
that is how.
there
Yes.
is a small typo in C alpha beta. If you see the second term, C alpha beta, dx alpha, dx beta. Yeah, here as well and the downstairs as well.
This one?
Yeah.
No, no, no. This is squared, no? See, this
Oh,
quantity is
okay.
squared. So
Okay.
you write this as C alpha beta dx alpha dx beta times C gamma delta or rho sigma dx rho dx sigma. Okay, that is the kind of quantity it is. Okay. So yeah, maybe this is a bad notation to write because it would give you an impression that this alpha beta and this alpha beta is same. Actually, they are not. So I should probably write C alpha rho. Yeah, maybe
Yeah.
C rho alpha dx rho x rho dx alpha times the other quantity. Okay, but if you read it here, it is correct. Okay, but because it is squared, dx is coming from one term like this and another term like that, and this is not dx. Otherwise it should
Yes,
have
sir.
become dx to the fourth.
Yeah. Yeah. Yeah.
Right? Okay, so I'll correct this equation because this alpha beta could be a bit confusing. Okay, I'll write it in terms of rho sigma, which will be kind of clearer. Okay, but metric component written in this form is correct. Okay, so this whole thing should be multiplied by dx alpha dx beta. Okay, fine. So now what we can do is we can take look at special situations to see what we would get. Okay, so for example, if you take k is equal to 0, then we should get a flat space. Okay, in other words, k is actually a measure of the curvature of the space. Fine. So one thing is kind of easy. If you take k is equal to 0, this term just drops out. G is equal to c. Okay, and in this particular case, we should be able to see d into d plus 1 by 2 isometries from the line element, line element of d plus 1 dimensional space. Okay, not if of. Okay, so the way it happens is the following: that a d plus 1 dimensional space was flat, right?
Yes, sir.
So here's a flat space metric in d plus 1 dimensional space, and because it is flat space, and we have seen that the Minkowski space has d into d plus 1 by 2 isometries, you should be able to get all those isometries for this space. Okay. Now you are in d plus 1 dimension, so you will get d plus 1 into d plus 2 by 2 isometries here. Okay, but not all those isometries are going to descend down on this surface. Okay, on this surface, subject all those isometries will survive on this subject to the condition that this equation is satisfied. Okay, so whatever are the isometries that you would get here, okay, you need to kind of bring them down to this space. Okay, so you are looking at only those class of transformations which not only keep the line element in the higher dimension invariant, but also leaves the embedding equation invariant. Okay, so those transformations corresponds to this set of transformations. Okay, this is one
Sir,
set of yes.
in D+1 dimensions, if one simply takes k to 0,
Yeah,
that doesn't make sense, right? Because
that is right.
dz
Yeah,
over k.
yeah, yeah, exactly. So you are actually at a particular point in that space, basically. Okay, right?
Okay.
You have to set z to 0 to get this thing sensible. So of course, what you do is that you don't set k is equal to 0. You take k small, compute the quantity, and then set k is equal to 0. Okay. So it's like how you embed a flat space inside a flat space. It looks like an odd thing to do, but you can do it very easily. In realistic terms, it is very easy. I mean, you can always embed a plane in three-dimensional space, right? It is just that like written in this form, it looks a bit odd. Okay, so what you do is that you take k small, embed, and then compute at the end of it, set k to 0. Okay.
Okay, sir.
Fine. So you get uh, you get the invariance in of the surface if you do look at the transformations of this guy. That x alpha goes to x prime alpha, which is a rotation of x alpha plus a transformation involving z, and z goes to z prime, which is kind of a transformation involving x times the scaling of z. Okay. If you take these equations, not moving, yeah, and demand that this set of transformations leave the metric invariant, okay, then it tells you that alpha beta component should give you C again. Alpha z component should be 0 because original metric didn't have that alpha z component, and zz component should give you another quantity k, which let's call it k prime. Okay. We want to ask a question: what are the solutions to these equations? Okay. So let's choose these transformation matrices that we have written down. Okay, so let's say r alpha gamma is not equal to 0, but anything which rotates x alpha to z is 0, and suppose r z z is equal to 1. Okay, if you do that, then you will find that anything which involves r beta z or z gamma, they will be set to 0. So this is trivially satisfied. Okay, here r alpha z beta z terms would vanish. Okay, and this quantity just tells you that k inverse is equal to k prime inverse, which means k is equal to k prime. Okay, in this case r z gamma would be 0, so therefore it just tells you that c alpha beta is related to c prime by just a rotation. Okay, so that is the equation. Okay, fine. Now this of course corresponds to rigid rotations in d dimensions. Okay, because this is how the metric would be transformed under a rotation. Okay, fine. You could do something else. Okay, and uh, that would be like, you could choose a transformation where r alpha z is equal to a alpha, and r z alpha is equal to something quite complicated like that. Okay, k times c alpha beta times a beta times delta, and r z z is equal to this quantity. Okay, and r alpha gamma to be a quantity like that. Okay. Now suppose you put this choice back into this these equations that we had written down. Okay, you get a bunch of equations. Okay, for C alpha beta. Okay, you can kind of massage these equations. You can see that, like, there exist terms which involve two A's. Okay, so look at the product of this expression. There is a A rho and a eta, and then there is a term here which is A alpha A rho multiplying this delta, and this delta multiplying this A alpha A rho. So there are terms which are quadratic in A, and then there exists one term which is quartic in A, which is A alpha A rho times A beta A eta. Okay, so if you kind of collect all these pieces, you get an expression which looks like this. Okay, so there are terms which are quadratic in A, here, here, and here, and then there is a term which is quartic in A. Okay, fine. So one can try to further simplify this expression, and you can show that uh, you get an equation which is like get two sets of equation basically, and uh, you can show that like that those equations can be written in this particular form. Okay, now so what you're trying to do basically here is to kind of determine B, okay, where B was a parameter which was sitting out here, okay, and you want to determine that parameter, and what you find is that, like, you know, after massaging these equations, the parameter B takes the form like this. Okay, so we haven't done anything actually. What we have done is basically you look at this expression, there are lots of delta sitting around. Okay, so you just collect those deltas and replace, you know, you replace uh, say beta by delta here, and sigma by gamma there, and stuff like that, and get rid of many of those guys. Then you will find that all the terms that you have, like for example here, if you replace beta by delta, you get C alpha delta. Okay, and this one gives you C gamma lambda. So what you do is that, like, you know, you collect those pieces and bring them together. All the terms are quadratic in C. Okay, indices are kind of looking different, but don't worry about those indices, because uh, you know, there are lots of dummy indices which you can kind of swap around. Okay, once you do that, then you get an expression which looks like this, times various factors of B's and A's. Okay, there are terms which are quadratic in A, which are minus 2 times B, these two pieces, and then there's a term proportional to B squared which is quartic in A, so therefore there's a 2A's here and 2A's inside, and then there is a term which is like this, okay, which is written out here, which is independent of B. Okay, and you have to set this to 0, and since C is a metric on the space which is non-trivial, and you want A transformation to be non-trivial, this parenthesis should vanish. Okay, so this is just a quadratic equation in B. Okay, and you can kind of solve this equation to find B to be this quantity. Okay, so what we'll do is we'll choose a negative sign here. Okay, and if you choose the negative sign, then you can do the following thing, that if you choose a negative sign, then you can show that the transformation yeah, sorry, I meant that show that at x alpha equals 0, okay, this transformation would reduce to a transformation like this. Okay, so that is not a very difficult thing, because all we have to do is to take B and put it into the expression that we wrote down. Okay, sorry for kind of going back and forth, but here, okay, so at x equals 0, you'll have to kind of determine how the function would look like, okay, by determining all these quantities, r alpha gamma written in this particular form, plug the value of B in and put it in. Okay, so you get an expression which looks like this. Okay, you will of course set x beta to 0, but you don't have to do that. All you have to ask is that what does this transformation look like, okay, in the neighborhood of x equals 0. Okay, and all you have to show is that this transformation is actually translation, although it looks very complicated. Okay, fine. So So what happens to, like, the two transformations that we looked at, one was the translation, the other one was the rotation transformation. Maybe I should just step back a bit. Namely this one, R alpha gamma not equal to 0 and rest always 0. This was the rotation transformation, rigid rotation, and this is the translation transformation. The translation appears to be more complicated than rotation in this particular case, but nevertheless, once you kind of substitute the value of B, you will see it's kind of trivial. Okay, so both of them put together will give you d into d minus 1 by 2 rigid rotations and d transitional isometries, and when you combine those, okay, you get d into d plus 1 by 2 isometries. Okay, these are all infinitesimal transformations. Okay, because we are just looking at in the neighborhood of a particular point. Okay, but we have just seen that that even if it is an infinitesimal transformation, finite transformation can be generated if you know the killing vector and its covariant derivative. That's all that you really need to know. Okay, if you know the killing vector and its covariant derivative, you would be able to determine the Riemann tensor, and then using Riemann tensor, killing vector and its derivative, covariant derivative, you should be able to move the killing vector from a particular point to another. Okay, fine. So given the fact that these are isometries, would also imply that they should leave this K and the C invariant, because isometry leaves the metric invariant. Okay, fine. So what we have found by doing this transformation is that not only that the embedding space metric is left invariant, but these transformation also leaves the hypersurface defined by the algebraic equation C alpha beta x alpha x beta plus K inverse times Z squared is equal to K inverse kind of equation. Even that equation is left invariant. Okay. As a result, the induced metric on the surface, which was written earlier, which was where is it? This one, not this one, or let's put it this way, this one. This induced metric therefore would be invariant because C is left invariant, K is left invariant, and the embedding space metric is left invariant. Okay, so therefore G alpha beta is form invariant under this transformation. Okay.
So to explicitly see this, one can just put primes on x's and c's and k's, and k prime is k, c prime is c, and x prime, for x prime we use this transformation.
Use this transformation, exactly. Okay, this and the other one. Okay. But like, you will see, once you substitute the value of b here, it's trivial, as to why it's a translation. Okay, so here's an exercise. Using the induced metric, which is this, I need not have gone back actually, you can show that the Riemann-Christoffel connection can be written in this particular form. Okay, so it is just x alpha times g beta gamma. Okay, fine. So next exercise would be to take this as a Riemann-Christoffel connection and derive the geodesic equation. Well, you can substitute this, but you can take this metric and derive the geodesic equation and see that you get gamma to be exactly same inside the geodesic equation. Okay. Then of course you use that geodesic equation and solve it. Okay. Now the metric is not so simple because although C alpha beta is constant, G alpha beta is not. Okay. But nevertheless, just a second. Nevertheless, the geodesic equation would simplify because the Riemann-Christoffel connection is simple. Okay, so because of that, you should be able to solve the geodesic equation. Okay, The other thing which is part of the exercise is, given that you know what is gamma, try computing the Riemann tensor and show that Riemann tensor actually satisfies this condition. Okay. Okay. Fine. Now there's some typo again. Okay, so suppose we choose Euclidean signature for the time being, okay, just for understanding how these metrics are going to look like, okay, and choose C alpha beta to be diagonal, okay, uh, and uh, and choose it to be diagonal with 1 over k, 1 over mod k as a kind of coefficient, okay. Then you can check that the metric would actually reduce to 1 over k times dx squared plus x dot dx whole squared upon 1 minus x dot x. Okay, this is what will happen for k greater than 0, and you would get a minus sign here and a plus sign there. Okay, if k is less than 0. Okay, fine. So now you can see that, like, if k is greater than 0, then the mod x value is bounded from above, because there's a 1 minus mod x squared sitting in the denominator, right? So if mod x is greater than 1, then you are in trouble. In fact, you cannot cross mod x greater than 1, because mod x less than 1 to mod x greater than 1 involves a singular behavior. Okay, so mod x is kind of bounded if k is greater than 0. But if k is less than 0, there is no such bound. Okay, mod x can be anything. Okay, fine. So, so if you try to ask what is the embedding space metric, then embedding space metric, because C alpha beta was just 1 over k times delta alpha beta, and if you take k to be positive, then mod k is same as k, you find that the embedding space is actually flat Euclidean space. Okay, there is nothing special happening in the embedding space, because C alpha beta is just delta alpha beta. And the embedding surface equation would be just x dot x plus z squared equals 1. Remember, it was multiplied by C alpha beta times k. But C alpha beta times k simplifies, because C is 1 over k times delta alpha beta. So that 1 over k cancels out, particularly for k greater than 1, mod k and k are same. And delta alpha beta is just soaked up into this dot product. Okay, fine. But this is the equation of sphere, right? So x takes d value plus z. So this is a d plus one dimensional equation. Okay, but d plus one dimensional number of variables with one equation. So therefore it must be a d dimensional equation. Okay, so this is the equation for d dimensional sphere. Okay, fine. So therefore, whatever we have computed, yeah. For example, this metric for k greater than 0, okay, is actually a metric on the sphere, right? Because the embedding space equation is this, okay, and embedding surface equation is this, which is the equation for the sphere. Okay, fine. So here's an exercise. This is a metric on the sphere now, okay, which I have just argued that. Okay, take this metric and solve, of course, write down the geodesic equation. Okay, and once you write down the geodesic equation, try solving it. Okay, now sphere is not a very difficult space, right? we in fact know how the geodesics are going to look like. Okay, so but written in this particular format, okay, it looks like a little different set of variables. Okay, use this and try to set up a geodesic equation and solve it. Okay, now you do after having done that, you can do one more thing. That suppose you set the affine parameter. Remember, the geodesic equation has a affine parameter d2x by d lambda square plus gamma whatever times dx by d lambda kind of stuff. So suppose you choose lambda, which is the affine parameterizing the geodesic, you set it equal to 0 at the north pole of the sphere. Okay. You would, after having obtained the solution, you could ask a question: what would be the value of lambda when you are at the south pole? Okay. So it's quite a kind of, it's not a very difficult thing, but instructive exercise. Okay. The other thing is the following: that suppose you look at this metric, then if you take mod x is equal to 1, which is like x dot x equals 1, then it has coordinate singularity. Okay. Now the thing is that like x dot x equals 1 in our sphere equation naturally means that z is equal to 0. Okay. So at z equals 0 or x dot x equals 1, you know, the metric seems to be singular. What one wants to show is that check is whether the metric singularity of the metric is real singularity or whether it is just a coordinate singularity. Okay. By coordinate singularity, I mean that you can change the coordinate and show that nothing special has happened at that point. Okay. So what one can do is that one can just continue beyond this point. Okay. Remember, Z had to solve a quadratic equation, which was 1 minus x dot x kind of equation. Okay. You have an equation like this, then Z is equal to plus or minus square root of 1 minus x dot x. Okay. So if Z is taking positive values, okay, then as you approach x dot x equals 1, Z would vanish. And if you go beyond that, then Z would change sign. Okay. Now remember, even if Z changes sign, this equation has no sign because it involves Z squared. Okay. So therefore, what happens is that like if you want to go beyond this point, okay, all you need to do is to just flip the sign of Z. Okay. So you can smoothly continue your geodesic beyond x dot x equals 1 by just changing the sign of Z. Okay. Is that fine?
Yes, sir.
Okay. So now what we could do is we could ask the question: what happens if k is less than 0? Okay. Now, if k is less than 0, then the equation is a little different. Now, what you have is 1 plus x dot x in the denominator. Sorry, this file
So
has
no
become
need to
too big.
go that back.
Yeah,
I remember that. Yeah.
Yeah. The file has become 270 pages, so it is kind of just slow in loading. Actually, that is a problem. So because of this, there is no coordinate singularity anywhere. X dot x is always positive because it's kind of mod square of the vector. Okay. So this geometry with k less than 0 has nothing special happening at any point for any value of x. Okay. Good. So we could ask a question that what is the embedding surface for this space for k less than 0? Okay. And the answer is this equation. Okay. Minus x dot x plus z square is equal to 1. Okay. And of course, this relative sign clearly tells you that this geometry is hyperbolic. Okay. As against the previous one, which was spherical. Okay. Fine. Now, embedding space metric, of course, would look like this. It's a dx squared minus dz squared. Okay. Remember, there was a relative sign always between the metric versus the terms that you have written down. Okay. So clearly the embedding space has Lorentzian signature. Okay. And in that Lorentzian signature space, you are embedding a Euclidean hypersurface. Okay. So the surface that you are, the metric that you are writing down on this hypersurface is still Euclidean. And why is that? Because what you are doing is that you take this equation, write down z squared is equal to 1 plus x dot x, take a square root of that, which is plus or minus square root of 1 plus x dot x. Okay. Write down dz using that. Given z, you know what is dz. Use that to write down dz squared. Okay. So you can write down this expression. You have gotten rid of dz actually. Okay. And written everything in terms of x's. Okay. All you need to show is that the metric that you get, okay, this term, in spite of having a minus sign here, does not overwhelm the factor sitting around here, and therefore the metric always have the same signature. Okay. So that is, and therefore, if it has the same signature, then it's a Euclidean geometry. Okay. So that is the other solution for k less than 0. Okay. Now let's do something different. Remember, we were doing all this analysis by assuming that the space is Euclidean. Okay. Now let's kind of abandon that and look at the four-dimensional space, which is Lorentzian in signature. Okay. If the space is Lorentzian in signature, then you write down C alpha beta. Remember, we had written down C alpha beta to be delta alpha beta at some point.
Delta alpha beta by k in, yeah.
Yes, here. Okay. So that was because we are working with Euclidean signature. But now if you are working with Lorentzian signature, you can't use delta alpha beta, but you can use eta alpha beta. Okay. So that's what we'll do. We will say that C is eta alpha beta, and if you do that, then the metric on the hypersurface would look like this. Okay. It's the same metric, just replace C alpha beta by eta alpha beta. Okay. And we know that eta alpha beta was plus sign for coordinates and minus sign for time. Okay. So that's how it's going to appear. Okay. Fine. Now there's a series of exercises that I'm just going to list here. Okay. So first thing is that do a following change of coordinates. It looks horrible, but it's doable. Okay. So define. So remember, you have a metric written out here. Okay. You write down t to be 1 over square root k times r prime squared by 2 times k times cos hyperbolic square root of k times t prime. So we have new coordinates r prime and t prime. Okay, plus 1 plus k by 2 times r prime squared times sine hyperbolic function. Okay, and use x vector, transform that to x prime vector times exponential of square root of k t prime. Okay, so here is our original metric with the Minkowski signature. Okay, and we do this coordinate transformation. Okay, r as is r prime is just kind of, I should have put primes on this, x prime dot x prime basically. Okay, fine. So once you do that, then you can show that the metric this becomes a metric which looks like this. Okay, this is a metric that we have written down just above here. Okay, fine. So you can show that this metric can be brought into this particular form. Okay, and you can see that there is a dt prime squared piece with a minus 1, and then there's an exponential e to the square root k times t prime times the spatial part of the metric. Okay, this is what is called the Destro metric. Okay, so the space described by this metric is what is called a Destro space. Okay,
And this is the accelerating flat universe, right?
Yes,
I mean
this is the
expanding.
exponentially
Accelerate.
expanding. Yeah,
Yeah.
yeah. So it's exponentially expanding flat space. Yeah. So that is the
So,
De
sir,
Sitter metric.
the AT that we have in the Friedman Robertson Walker
Yeah.
metric, that can be chosen. I mean, with
Yes.
different functions.
Yes. Exactly. Exactly. But De Sitter is a very specific choice. As you can see that it's an exponential function. AT that you use in Friedman Robertson Walker, it doesn't have to be uh, always exponential. In fact, it is not. Right? When it is matter dominated, when it is radiation dominated, correspond to different configurations, different behavior of A. Right?
Okay.
So De Sitter is a very specific behavior, which is exponential growth. Okay, not just simply accelerated growth. Okay,
Okay, sir.
right. Because accelerated growth means like AT can go as t squared and it is still accelerating, right? Because the second
True.
derivative of
True.
A is not zero. But this is like exponential. You take any number of derivative and it is still kind of growing exponentially. Okay, so let's do one more coordinate transformation. So we have arrived at this metric. Okay, we do another complicated transformation. T double prime is equal to T prime times T prime minus 1 over 2 root k times log of this function. Okay, 1 minus k times x prime dot x prime times exponential of 2 root k T prime. Okay, it's the same function. Okay, and x double prime as x prime times exponential. Okay, this is pretty much like this kind of expression. Okay, it's just that like you go from x to x prime this way, and then you go from x prime to x double prime by doing the same stuff. Okay, so if you do this transformation, then check that you will get the metric which takes the form like that. Okay, now you notice one difference here, that unlike the previous form of the De Sitter metric, which was exclusively time dependent metric, okay, this form has no time dependence at all. Okay, so this is what is called the time independent De Sitter metric. Okay, so it depends upon which kind of problem that you want to solve in say De Sitter space. Sometimes you use time dependent metric, sometimes you use time independent metric. Okay, in fact, uh, one may think that like that if you want to compute some time independent quantities inside the De Sitter space, it may be the time independent metric which will be useful. Okay, uh, some experience with De Sitter metric shows that that's not the case. Many times the time dependent metric is easier to deal with even to compute time independent quantities. Okay, but yeah, so there are certain quantities for which this form of the metric is useful. Certain other quantities, the time dependent part of the metric is useful. Okay. Okay. Let's consider the next thing, and that is consider the symmetric subspaces of the space-time. Okay. So, for example, if you are looking at spherically symmetric space, okay. Now, when I say spherically symmetric space, we are only looking at the spatial part of the metric and demand that it is spherically symmetric. Okay. So, if it is like that, then the metric would take a form which is like this, that it should be fr times dr squared times gr times d theta squared plus sine squared theta d phi squared minus dt squared. Okay, where fr and gr are functions of only r. Okay, and these are functions such that this metric solves the Einstein equation. Okay, so that is a condition that we'll have to kind of impose. Okay, fine. So what is the function fr and gr depends upon what kind of equation that you have written down, whether you have written down vacuum Einstein equation or Einstein equation with cosmological constant with positive sign, negative sign, or Einstein equation with matter energy momentum tensor on the right hand side. All that would determine what these functions are. Okay, so that's why they are only subject to solving the Einstein equation. You could have spherically symmetric space-time, okay, which is little different from this one. Namely, only thing that you have is d theta squared plus sine squared theta d phi squared piece, okay, which is the statement about spherical symmetry. But dt squared, dr dt, dr squared, all these quantities could be not only functions of r, but could also be functions of time. Okay, so this small distinction, spherically symmetric space versus spherically symmetric space time. Okay. Now, of course, all these functions gtt, grt, grr, and g are subject to solving Einstein equation. Okay. So again, as I said, depending upon what is the form of the equation that you have, what is there on the right hand side, this function will depend on that. Okay. Fine. So let's look at the next set of metrics, and that is spherically symmetric homogeneous space. Okay. Now, since the space is spherically symmetric, you know that the metric should contain a d theta squared plus sine squared theta d phi squared. We have already encountered this in two earlier spherically symmetric examples here as well as here. So we know that spherical symmetry would imply the metric should have this factor. Okay, but the space is homogeneous. Okay, the homogeneity of the space tells you that GRT has to be 0. Okay, and not only that GRT is equal to 0, but GRR and G should also be functions only of time. They cannot be function of space, because if they are function of space, then transition invariance is gone. Okay, fine. So besides setting GRT to 0, we also have to say GRR and G are only functions of time. If you do that, then you can look at this metric. You set GRT to 0. You say that this is a function of time, this is a function of time, and this is also a function of time because of the transition invariance. But if GTT is a function of times dt squared, you can just redefine time. Okay, you define that as GTT times square root of GTT times dt is equal to dt tilde. Okay, and write everything in terms of dt tilde and set the corresponding g t tilde component of the metric to be just 1. Okay, so that's what I said, that you can just use some general coordinate transformation to set this quantity to 1. Okay, I'm calling this to be 1 because minus sign has been pulled out explicitly here. Okay, otherwise I would have just called it GTT equals minus 1. Okay, so what we get is that GTT component is written 1, GRT component is 0, and these are just functions of time. Okay, these functions of time tells you that there is a GRR as a function of time, and G spherical part is also a function of time. So just use that to write down the metric in the following form. Okay, so here's an exercise. Okay, that starting with this metric, show that spherical symmetry and spatial homogeneity would give you a metric which looks like that. Okay, so you need to kind of massage this stuff, use x's to be Cartesian coordinates, replace those Cartesian coordinates by polar coordinates, and check that this form of the metric is going to take a form like that. Okay, so that's an exercise. Okay, and this is of course the famous Robertson-Walker metric. Okay, in Robertson-Walker metric we use, conventionally we call it A of t. When we'll do cosmology, we'll call it A of t, but right now it's like this. Okay, so I think what I'll do is I'll stop at this point and we'll take up from here. Okay, so what we have done so far is we have just looked at class of solutions to Einstein equation, not necessarily vacuum Einstein equation. Einstein equation may be with cosmological constant, and and what we have shown is that there is this class of solutions with a high degree of symmetry. Either they are maximally symmetric or they are spatially maximally symmetric, like Robertson-Walker metric with spatially maximally symmetric. Okay, if you use this class of metrics, solution to Einstein equation is kind of easy to show, that these solve Einstein equation in the presence of sometimes zero cosmological constant, sometimes positive, sometimes negative cosmological constant. Okay. What we'll do next time is to look for a solution which is again symmetric, spherically symmetric, but little more non-trivial than this. Okay. So that is what we'll do in the next lecture. Okay.
That would be the Schwarzschild solution, right?
Schwarzschild, yeah. So we will try to do Schwarzschild in two different ways. One quick solution, and the next one will be kind of work out the whole stuff. Okay.